Okay, Bismillah Rahman Rahim. Dear students, today we deal with the graphs. We are done with the trees and we have seen a tree like this, okay, which happens to be a binary tree. And is this a graph or it is a tree? I will say it's both. Why? It's a tree because it doesn't have cycles, okay, and it's connected, and that means from the root you can go to the any node. You have a path. But if it is like this, it's unconnected. It's not a tree. Basically, it's a two trees because it's unconnected. But if I say, is this a graph? I will say yes, because what a graph is a set of vertices and set of edges. Here we got the vertices as a nodes, and we got the edges like this. So tree is also a graph, okay? But a tree is a special kind of graph because we don't have cycles in it, so it is an acyclic graph. So if we talk of a graphs, basically, a graph can be cyclic, a graph can be acyclic. The graph can have a lot of types. Okay, a graph can be weighted, means you have a graph. For example, this is a path, this is an edge. An edge basically maybe some sort of cost, some sort of weight in terms of maybe sometimes a length between the two stees, sometimes a airfare between the two stees or whatever. So we can have a weights. So we can have unweighted like this. We can have directed. So you can have weights or unweighted. You can have unweighted. You can have directed. So if you talk of this tree, this has direction implicit. You don't give direction like this, okay, even though we can give because it is like this, but it has an implicit direction. So it's an implicit directed graph. And so we can say a tree is an acyclic directed graph. So it's acyclic, it doesn't have cycles, and it's directed. But we don't give direction, but it has directions. So if you give directions, so graph will become directed. So that means you can go from this point to this point, but not vice versa, unless you don't have an edge which says like this. Okay? So a directed graph, also called as diagraph. And a graph, if it doesn't have a cycles, is called directed acyclic graph, called a DAG. Because we got a third called, if you got acyclic graphs which do not have cycles, and we're gonna have cyclic graphs which has cycles. And if we combine these two together, we got DAG, directed acyclic graph. Okay. Okay. So we got the set of vertices and set of edges. But if you connect them together, okay, if you have cycles like this has got a cycle here, it's no more a tree. It is a graph. It's no more a tree if you got a cycles in it. So there is no sibling connections in a tree, but in a graph we have sibling connections. Okay. Now a graph may be connected. That means you can reach to all the nodes. Okay. Then it's connected. If you can't reach to a particular node, it's unconnected graph. Okay. If you got a connected acyclic undirected graph, so you got like this. This is connected. I'm gonna reach to every node. Now I'm not having any cycles like this. I'm not having any cycles. Okay. I'm not having any kind of cycles here. You can go like this to make it a graph. Not necessarily I'm talking about binary trees only. Now if you're connected, this is connected, you can go to any node you like. Okay, we have a path. Undirected, we don't have a directions. You can go from this way or you can go from this way, doesn't matter. It's called a free tree. But the condition is it should be acyclic, it should be connected, it should be undirected. So we got a free tree because you can put up anything and call it as a root. You can put up this and say, hey, you pick this and call it You pick this in your hand, you say this is the root. You pick this in your hand, this becomes a root. You pick this in your hand, this becomes a root. Or you pick any diamond node, it becomes a root, and rest of the tree hangs with that root. So this is called as a free tree. Okay. In a graph also we can have the self loops, can edge to itself. Okay, path which destination and source are the same. We may have sometimes a graph which are parallel edges, but we don't take them, we don't call them as a graphs as such if we don't explicitly mention, because parallel edges are not allowed, for example. Okay. Now we also have the degree associated with the vertex. We call them a degree, and degree can be in degree and out degree in case of a directed graph. That means how many edges are incident on the vertex and how many edges are going out of the vertex. If you have undirected graph, for example, you can see how many edges are incident on it. So like 1, 2, and 3, I can call it as because the loop is counted as 1. Okay, so I can say 1, 2, and 3 is the degree of this vertex. But if it is directed, we got two guys, we got in degree and we got out degree. Okay. I'm gonna make this like this. So this guy got an in degree 1 and out degree 1. This guy got in degree 1, out degree 1. This guy got in degree 1 and out degree 1. Yeah. Is this guy in degree 1 but out degree is 2? Sorry, out degree is 2, in degree is 1. This guy got in degree, out degree 1, and this guy got out degree 1 and in degree 2. Okay, so this is the degree of the vertex. Now this is a little visualization of directed and undirected graphs we got here, right? Now this is my directed graph. On this side I got undirected graphs, okay, because of the directions, and on this side we don't have directions. And this one is directed but acyclic. They don't have cycle. You could see the arrow is on this side and arrow is on this side, but arrow is on this side. So if you want to go to A to B, B to D, now you can come back to A. If you could have come back to A, then it's a cyclic. It's acyclic. Is undirected is again acyclic. So if in undirected you're gonna be acyclic, it's gonna be tree then. Okay, it's like this. And in cyclic we got a cycle. You can go from the A from here, you can go to the B, then you can go at a cycle, you can go from this way and you can go this way, you reach your A back. So this is a cycle, this is our cycle. This is cyclic, and this is also cyclic, so you can have a cycle here. You can also have the edge labels or weights. Okay, this is directed one, and you got a weights here, 3, you got a 4, you have 5, you have 6 as a weight edge, and you have here also edges 2, 6, 3, and 3 as my weight. Okay, so the question is why we use graphs. There are thousands of things why we use graphs. One of the things is like we can get some. Now what I have is, for example, I got a channels. We got 4 channels and we got 6 programs to assign. And I'm seeing the timing. A channel P1 is running from the 10 to 11, and channel 2 is running from 10:30. That means when channel 1 is running, program 1 is running, you cannot run program 1 and program 2 on the same channel because they have a timing clash. Is it? So it finishes 11 but it starts 11 10:30. So that means it's got a timing clash, right? Similarly, if you cannot assign at that P6 because P6 also has a timing clash. Now this guy and this guy can run because it's 11, it finished 11, it starts at 11:15. So if you run this on channel 1, this is also on channel 1, no problem, because it finishes, this starts. Okay, now this has a conflict with this guy also. Okay, this is a conflict, this doesn't have a conflict with this. 11:30 finishes, 11:45 starts. Okay, this guy has a conflict with this guy doesn't have a conflict with this guy, and so on. So we map the conflict edges. So we map first, make these processes as nodes. Okay, we call them, this is for example P1, this is my P2, this is my P3, then we're gonna go P4, then we have P5, and this is my P6. Okay, starting from P1. Now P1 has a conflict with P2, so drop it here, edge, drop in conflict edge. P1 also has a conflict with P6, is it? P1 has a conflict with the P6, so drop an edge. P1 has conflict with some other guy. P1 has conflict with P2, yes, not with P3, not with P4, not with this P6. Okay, now start with P2. P2 has a conflict with P1, we have done it. P2 is a conflict with the P3, P2 is conflict with the P3, so this is a conflict with the P3. Okay, and P2 has a conflict with P6 as well. Okay, now P3 has a conflict with as done, it has also conflict with the P4. He has a conflict with the P4. This guy has a conflict with P4, and P4 has a conflict with P6. P3 also has a conflict with P6, right? P4 is a conflict with P6. Okay, and P5 has a conflict with P6. Okay, and also with the P4, also conflict with P4. So you got the graph like this. So if you're assigning the channel 1 to the P1, so channel 1 C1 to the P1, now you cannot assign this to the P2, you cannot assign channel 1 to the P6. Okay, say for the P2 you give channel second then. Okay, now if you give channel P2 channel second, you cannot give channel second to the P whatever this is, P3, or you cannot give this to the P6. So instead you can give it the C1, because there's no problem giving C1 to the P3 because P3 does not have a conflict with the P1. Okay, so you can give C1 to the P1 and this guy. Even you can give C1 to the P5 because P5 doesn't matter, does not have a problem with this thing. Okay, so you can assign C1 here also. You can give C2 here. Okay, and what about the P4? P4 is a conflict with C3, so you cannot assign it the C1 channel. Okay, it does have a conflict with this guy. You cannot assign C1 to this. Okay, you can assign C1 to this because C1 is already being assigned to the P3 as well as P5, so you can go for C2, no problem, because if you go C2 to this guy, because it doesn't have a problem with the P2. Okay, it has problem with the C3, so you cannot give assign C1. It is assigned problem with the C5, you can get C1, but you can get C2 here. And P6 is a problem with the P1 as well, C2 as well, P2 as well, P4 as well, P3 as well, so everybody. So you have to give new channel to it, say for example C3. So I got only 3 channels assigned, even one channel is left out, so you can give it to the other guy. Okay, so by this we understood how to resolve the conflict of channel allocation. This is one of the use of graphs. We may have enormous use of graphs. For example, and another problem is, if we add a page here, another problem could be like we have the stees here. Okay, this is one of the problems we will solve also later on. We got some sort of stees and they connected with some air, road and train maybe, and they have some paths in between, and there are multiple paths. You can go from this way to that way in a multiple ways. A lot of roads you can go in from one way to other. Okay, and you can go this way to this. You may have some other paths also. Okay, the question is which one is the shortest path, because you may have given some weights in terms of cost, in terms of distance, in terms of whatever. Okay, and Now for example, point this A to point this, which one is the shortest path? You have to choose them among many paths we have. So this is also the problem which we solve later on, shortest path algorithm like Dijkstra algorithm will do, and this is also the problem resolved by mapping things in the graph. So graph has a lot of applications. It's everywhere being used. Discrete maths, wherever you go, you will see the graphs, and you see engineering. You see like for example, we got a motherboard, a chassis, and you have laid up a circuits. Now you want to see that you want to lay in such a manner these wires so that they will not overlap. This can also be done by using the graphs. Okay. Now the next question which comes into mind is how to represent a graph. So graphs can be represented either two ways, right? A graph representation. So we say graph representation. Okay. So graph is basically two. One is, as we know, sequential, and we got linked list. So you can represent your graph using linked list, or sequential means arrays. So in arrays, we got two guys. One is the adjacency matrix and one is incidence matrix. One is the adjacency matrix and one is the incidence matrix. Okay, and in the linked list representation we got two guys also. One is the adjacency list and one is the multi-list representation. Multi-list representation, whatever. It's also called as direct representation. Okay, so let's see how we represent sequentially as well as linked list. The adjacency matrix and incidence matrix we take up first. Okay, so in the adjacency matrix, what we do is, if we got an edge, for example, we represent here the on one side we represent the vertices, and on the other side we also represent the vertices. Okay, so for example, we got the vertices C1, C2, C3, so we say C1, C2, C3, C4, and on this side also. Or we have names here 1, 2, 3, 4. So also 1, 2, 3, 4, 7, 8, and on this side 8. And if we have an edge from 1 to 1, for example, if we have a loop like this, then you might have here 1. So 1 to 2 is an edge, so 1 to 2 is an edge, write 1 here. 1 to 3 is an edge, write 1 here. 1 to 4 is nothing, 1 to 5 is nothing, so put of zeros there, and 2 to 1, yeah, we got 1, and so on. Okay, so if there is an edge between the two, 1, 1, 1, 2, 2, 2, 2, 3, 2, 4, or somewhere else, put a 1, and if we do not have, put up a 0. This is called as the adjacency matrix. Another way of representing is called incidence matrix. Okay, this is the incidence matrix where we got the vertices and we got the edges. So I would say adjacency list where we have the vertex versus vertices, and square vertices, we got n square matrix there. But here we got the vertices and the edges. We say what? We got three things here: 1, -1, and 0. Okay. If the matrix, the value of the matrix are -1, 0, 1. Okay. If the edge starts from, say, for example, here, if you say V1, the edge starts from V1 to V3. Okay. So the edge E1, if you talk of E1, it starts from V1 to V2, right? V1 to V2. So edge E1 have then 1 from the V1 start point. Okay, it will have the -1. What has happened to it? Okay, 1. It has the -1 to the where it lands. It's landed to the V2, so -1 will be here, and elsewhere it will be 0. Similarly, a second starts from v2, so it has the 1 here, and -1, where is the destination is v1 and 0 elsewhere. Similarly, e3 is from v1, so 1 on here, up to v3, so -1 here, rest are 0. e4, similarly, e4 is, say for example, from v4, so 1 should be on a v4, and v3 we got -1 and 0 0 and so on. So this is another way of representing our graph, and back to the sequence representation. Okay, but we have problems with the sequence representation, that we may have the sparse graph, wherein we may have lesser number of edges, so than the vertices, and we may come up with the lot of empty spaces in an array. So we have come up that a graph matrix is a good and simple way to represent our graph, but all graphs do not have high degree of connectivity. So if we have n nodes in a graph, we have, how many we have n. What has happened to it? Okay, we have n into n minus 1 slash 2 undirected edges. This much undirected edges we get. Okay, if we talk about n directed edges. Okay, and for the matrix, if you say adjacency matrix, we got n square matrix. So for example, if we got here 1 2 3 4 vertices, we got 4 into 4 minus 1, that is 4 into 3 divided by 2, that is 6 undirected edges, and n square is got 4 cos square, that's going to be 16. So 16 versus 6 edges. So if the connectivity is lesser, we will have a lot of space is wasted. Okay, so that's why we move on to the next, that's called as a linked list presentation, what's called as adjacency list representation. Okay, that we'll do in the next video.